Okay, so this is where we left off after the first course, and we have our terrain aligned and land cover aligned. And so now we can move forward with the next steps and finish this analysis to identify vineyards. So as a refresher, we have gone through extracting our data sets and aligning the rasters. And what we're going to work on first thing this morning is I'll show you how to generate both slope and aspect from the DTM. We're then going to use this reclassify tool to reclassify the slope and the aspect and the land cover into categories that are meaningful for identifying a vineyard location. So with slope and aspect, these are going to be processing algorithms that you'll find in the processing toolbox for QGIS. And they're going to be in this raster terrain analysis tool set. So there's quite a few things you can generate from a DTM. The first we're going to work with is slope, and this slope tool in QGIS produces slope in degrees. I'll show you another one that also allows you to compute slope in percent if you need to do that. We're then going to generate aspect, and every pixel will have the cardinal direction that that slope faces. There's also some other interesting tools in here. There's ruggedness index, which outputs something similar but different than slope. It's a measurement of heterogeneity or how different the terrain is or surrounding the pixel. And then you can also generate a hill shade image. So we're using just the rendering tools in QGIS for that, but you can also generate a hill shade image with that tool. So there's a number of things in there, and this is the link to the documentation for all of those. So first we're going to calculate slope, and slope is calculated using this function where you take the arctangent of the change in elevation over the change in distance horizontally across the surface, and that gives you the slope in degrees. And when you're computing slope, what the software is doing is what's called a moving window or a kernel analysis, where if we start with this one pixel here in the upper left of this raster, which we can say is a DTM, what it's going to do is compute the difference in elevation between this pixel and the 8 surrounding pixels. And it will then generate the slope based on those differences. So it's what's known as a moving window operation, because it will do this pixel by pixel by pixel throughout the, whoops, sorry about that. Get back to that. So it's going to move pixel by pixel to produce this slope raster. And one thing to be aware of is that if we take one of these edge pixels, well, we don't have the 8 surrounding pixels in this for this one. We only have, the 5 surrounding pixels. So there will be anomalies that are called edge effects on the edge of the raster when you do that. So you may get some outlying results around the 1 perimeter pixel of the output data set. So sometimes people will generate a DTM that's at least 1 pixel dimension bigger than their study area to account for this. We're not really so concerned about this for this analysis, but just wanted to make you aware that there can be issues that you encounter because of edge effects like that. So this is what the output slope can look like when it's styled, and we'll get, in this case, we have the steeper slopes as red and the flatter areas as green. After that, we're going to generate aspect. So this is the cardinal direction of the slope. And I will show you, since this is the numbers that will be assigned to the output aspect raster. So 0 and 360 will be a true north facing slope. 90 would be east, 180 south, and 270 west. And we have all the numbers in between. So since this is a circular range of values, we can generate what is known as a circular color ramp, where we start and end at the same color, and then so we can make this kind of an intuitive cool color for north facing slopes, make the south facing slopes a warm color like yellow, and then choose intermediate colors for east and west. And this creates a circular color ramp that can be a more intuitive way to display this kind of data. So I'll get back into QGIS and we'll go ahead and generate slope first of all. So in the processing toolbox, I'll find that in the raster terrain analysis section. And so I will double click on slope to open this up. And the important thing here is to pick the correct layer as the input. So we're going to use the terrain aligned that we used, that was the output of the alignment tool, so that the slope will also be aligned as a result. And I'll save this out again as a TIFF. And I'll just name this slope. This Z factor, I will leave at 1. This is in case you have a situation where your X and your Y are in different units than your Z coordinates. Here, we're dealing with UTM, and our Z coordinates are also in meters. So our X, Y, and Z coordinates are all in meters. And we can leave that at 1 to get accurate results. This is more used in countries that use imperial units, like the United Kingdom or the United States, where we may have the Z values in feet and the X and Y in meters. And in that case, you have to put the conversion factor in there to get an accurate result. But most places in the world, we can just leave that at the default value of 1 and click run. And we'll close. And here we get our slope output. And if I double click on this, look at the result, the data type is a 32-bit floating point raster. So this means that it stores decimal places and stores quite a few unique values. So this is why we're going to be running into the reclassify tool, because the slope values here have far more detail than we need. But that's typically the way slope is output. And so we can see the maximum value and the minimum value. So it ranges from 55 degrees to 0. And I'll just quickly style this. Instead of single band gray, I'll style it from maybe red to green. Red, yellow, green. And I'm going to invert this color ramp. And so we can, it looks like it's mostly green, but if we zoom into some areas here, we can see that there are some steeper portions in the study area as well. Okay, the next thing we're going to generate is aspect. Find it in the same tool set. And here we want the elevation raster to also be terrain aligned. Again, we can leave the Z factor at 1 for the same reason and save this out as aspect. So here it generated the aspect. And you can see that here it also didn't generate aspect for the flat slopes. These are lakes in our case, which are going to be unsuitable land cover types anyway. So that is fine, but the aspect here was not generated. There's another in the raster analysis Google tool set here. There's another aspect tool that you could also try. This might, this is a different provider. It may give different results. So it's always worth trying different tools to see if they give better results for your purposes. But for our purposes, the standard QGIS aspect tool is going to work fine. There's also a slope tool in this same Google tool set under raster analysis. And this one has a checkbox that you can use to generate slope as percent instead of degrees, in case you need that. So there are in QGIS, usually multiple tools that will do something similar because there are different data providers in the toolbox. But this aspect raster will work fine. And I'm going to open up layer properties and go to the symbology tab. And I'm going to apply a QML style that I provided you with the class, which is that circular color ramp. So I'll choose load style, go into the folder for this, and in styles, there's the aspect circular color ramp QML file that I provided. So you can open this up, and I can go into edit color ramp to see how this is configured. And you can see that we're starting both with color 1 and color 2 at the same blue, and then having the south facing slopes will be yellow and the west and east being intermediate colors. So that's how this color ramp is set up. So I can click OK. And so we can use this. I usually do this simply to make sure that the data looks correct. So I might, in this case, turn on just the hill shade below and give this aspect a blending mode of multiply so that I can see the terrain through it. Turn off that imagery below. And then if you zoom in, you can kind of get a better sense of how this is working. And you can see that this is a high point. And so this is the north facing slope in cool colors and the south facing slope in warmer colors. Okay, so now that we have generated those two byproducts of our DTM, we're going to reclassify them. And this is basically because there's more data in both the slope and aspect than we need. More information. They're both 32-point or 32-bit floating point rasters with this huge range of decimal values that go out to many decimal places of precision. And we simply don't need that much detail. So we're basically going to be aggregating these data into 4 categories that we do have information on related to building a vineyard. And so we're going to be reclassifying these from values of 4 to 1. So we'll be producing an integer raster from these, where 4 is the best conditions for aspect, for example, for a vineyard, and 1 is the worst aspect for a vineyard. And so we'll have both the slope and aspect output from the reclassify tool as integer rasters from 4 to 1. And so this is where we're starting to build this as an analysis for a vineyard. So I'll go back into the processing toolbox. And if I go into the raster analysis section, I will see the reclassify by layer and reclassify by table. Reclassify by layer would be where you're going to reclassify it based on values in another layer. Here we're going to use reclassify by table because we're going to build our own reclassification table to generate these. So I'm going to start with the slope, and I will input slope as the raster layer that I'm going to reclassify. And then you'll see there's this section of, this is the most important part, this reclassification table. So I'm going to click the ellipsis button to the next to that, and I'm going to build a table that has my reclassification rules. So here we're going to say that slopes between 6 and 15% are ideal. We want it to have enough slope, and we're also going to make that a south-facing slope combined with aspect, so that we have this vineyard kind of on a moderately south-facing slope as being ideal. So flatter slopes are going to be less ideal, and then slopes that are steeper than that will also be less ideal because they're too steep to farm on. So I'll start by adding a row, and I'm going to put in my minimum and maximum slope values here, and then this will be the output value for those. So for example, a slope between 0 and 1 will be one of the least ideal slopes. It'll have an output value of 1 for a vineyard. I'll add a second row, and this will go from 1 to 3 degrees, and this will receive a value of 2. Add a third row, and this will go from 3 degrees to 6 degrees, and this will have a value of 3 for vineyards. Then we'll get to the most ideal range of slopes, and this will be from 6 to 15 degrees. So this will be the optimum output of 4 for a vineyard. And then we'll add and go up to the highest slopes in our data set. We'll go from 15 to 20 degrees. We'll call this a value of 3, so a little less than ideal. 20 to 25, value of 2. And then finally, 25 to 60, which will have an output value of 1. So we kind of have our range where we have the best slopes, and then it declines as they get flatter and steeper from there. So go ahead and click OK. And now it says that I have a fixed table of 7 by 3. And then you can always go back in and edit that or change values if you need to. Okay, so the next thing to pay attention to is this range boundaries setting. Here we can use this default of less than value, less than or equal to max. For this, there are a number of choices in here. And sometimes it takes a little bit of experimentation to find which one is going to reclassify your results properly in terms of those range boundaries. And we're going to change the output data type to integer 16. And then I'm going to reclassify this or save this out to a reclassified raster. So I'm just going to name this slope underscore RC for reclassify. And so here I'm just going to use a little naming convention, underscore RC. So for me, that tells me that this was the slope that's been reclassified. So with that, I can check my settings and click run. And it reclassifies that slope. And what I can do is, since I have now an integer slope, I can change from single band gray to paletted unique values and click classify. And I can see that I have my output of 0 through 4 here, 0 being the flat parts of the lake and 1 through 4 being my ideal. And so I can actually change this from random colors to my red to green, where green is going to be most ideal, those with a value of 4, and the 0, 1, 2, 3 being less ideal. So next we're going to reclassify the aspect layer. So bring back up the reclassify by table tool, and this time going to choose aspect as the input raster. And we'll build the table for this. So with this, we have to remember that the values for aspect are ranging from 0 to 360. And what we're going to do is call the values that are south facing. So anywhere from 135 degrees to 225 degrees. And the south facing band will be ideal. Those will receive an output value of 4. And the northernmost ones will receive a value of 1. And we'll have 2s and 3s for the east and west slopes. So the first row, I can enter my ideal range here. So I'll give this a minimum value of 135 and a maximum of 225. And this will be optimum, so it'll have an output value of 4. Then I'm going to go northeast from there. So I'm going to go slopes of 90 to 135, having a value of 3. Then 225 to 270 going the other direction, also being 3. So we've gone east of south and west of south. And now we'll add the values that will be values of 2. So it'll be 45 to 90. And 270 to 315. And finally, the least preferable slopes will be north facing, will be 315 to 360. And 0 to 45. So this for aspect always takes a little bit of thought to, you might have to even draw it on the compass rose to figure out what your reclassification ranges should be. I'll go ahead and click OK. But I have, most ideal, and then going in either direction around the compass rose, my 2 3s, my 2 2s, and my 2 1s. So for this, I can use the same default range boundary setting. Again, I'll save this out to an integer raster and save this out as aspect reclassified. I'll use the same naming convention, aspect underscore RC. And I'll click run. So here I have my aspect reclassified. And again, I can style this as a paletted unique values renderer. You can see my 4 values, and again, style this from red to green, with the most favorable aspects being 4, and the least favorable being red. So I've got my aspect and slope reclassified and ready to input into the analysis. The last data set I'm going to reclassify is the land cover. So let me turn off this aspect and turn on this land cover. So remember, this is a categorical raster where we have values for each different land cover type. And here we are going to consider the grassland, the yellow, and the cropland, the pink, the areas that are ideal for a vineyard, or suitable rather, and all the other land cover types are going to be not suitable. So we're going to reclassify this into a binary raster of 1s and 0s, 1 being suitable for a vineyard and 0 being unsuitable. So we're basically going to be generating just a suitability land cover raster. So I'm going to bring up the reclassified table one more time and input the land cover aligned as the input raster. And again, I'll build my table. And this time I'm just going to be choosing each land cover class as minimum maximum. So 10 is going to be the first one, it's a tree cover, and that's going to have a suitability of 0. It's unsuitable. And then I'll add the next category, 20. That's also going to be unsuitable. And I'll get to values of 30, which is grassland, and I'll say that has a suitability value of 1. So this will be a suitable land cover type, as will 40, which is cropland. And I'll just continue. The rest are going to be unsuitable. Built up areas, 0. Bare and sparse vegetation, 0. $70 being water bodies, lakes, 0. $80 being herbaceous wetland. Is that right? I know that's permanent water bodies. 60, 50, 60. Yep. And then the last one being values of 90, which is the herbaceous wetland, and that'll be 0. So the only two that are going to be suitable land cover types are the grassland and cropland, 30 and 40. The rest I'm setting to 0. Click OK. For this, I'm going to change the range boundary setting to less than or equal to and less than or equal to for the min and the max. Since I have the same value for each, 10 to 10, 20 to 20, I'll change the output to integer and save this as land cover reclassified. Okay, so I can go ahead and run that. Click close. And again, I will style this with the same paletted unique values renderer. And I can again choose that red, yellow, green, where 1 are the suitable land cover types and 0 are the unsuitable land cover types. So you can see the forested areas come out as red. The pink and the yellow have been converted to green in this case. So we're basically going to use this as a mask when we get into the next stage of the analysis to remove unsuitable land cover types because they'll have a value of 0. So now that we have done those reclassifications, we can kind of revisit our workflow. So we're going to take those reclassified slope and aspect, and we're going to bring them into the raster calculator. And before we get into this, let me just talk about the raster calculator a little bit and introduce this. So the raster calculator allows you to do what is either known as raster algebra or map algebra. And it's where you can use mathematical operations to combine different raster layers to produce a different output. You can also use the raster calculator and develop expressions based on a single raster. And so this is a really useful environment for modeling. When you set up all your raster layers, you can then combine them. So for example, we can take the suitability of aspect and slope, the reclassified aspect and slope, and add those together and divide by 2. And then we get an output raster that would be the mean slope aspect. And so we'll have suitability based on those two factors. In this diagram here, we have a grid, two grids, and we're adding them together. So here we have a pixel value of 7 and one with a value of 2 in the next raster. And when we add those together, the output is 9. So we can add, subtract, multiply, divide rasters to get different outputs. I've used this, for example, I've modeled, I've been working on a public health analysis where I've modeled suitability for a public health outcome in one time period and then suitability in another time period. And I can subtract those two rasters to get the difference between the two time periods. So you can use this raster algebra for a lot of things doing raster analysis. Another way this raster algebra is used is just to do unit conversions. So especially in if you're dealing with data that has imperial units, for example, you can convert between units. So I could have precipitation in centimeters, and if I needed that in inches, I could just divide by the conversion factor to get an output in the other units. So if someone gives you a DTM with elevation values in feet, you can convert that to meters by using the correct conversion factor in the raster calculator and just get the output with different units. So when we do this, it's just going to adjust the numeric value of the pixels based on whatever mathematical operation you plug in. We can also use it for logical operations. So this is where in this example here with this elevation raster, if we say elevation greater than 1200, it's going to output a binary raster where wherever elevation is greater than 1200, they'll have a value of 1 in the output. And if they're less than 1200, it'll have a value of 0. So anytime we do this kind of operation, it's going to produce a binary raster of 0s and 1s. So we're going to be able to do this near the end of our analysis to figure out which pixels, we have a value of 1 to 4, and we're going to use 3.5 as the threshold that's suitable for a vineyard. And we'll be able to use this kind of expression to identify the areas that have a value of greater than 3.5. Some other things you can do Boolean operations. So this is the raster calculator here. And so you have all these different operators down here. And so probably the ones that are used most commonly are addition, multiplication, subtraction, division. But you'll see you also have Boolean operators, less than or equal to. You have and, or, if, and then cosine, sine, tangent. So you can use any of these in an expression against a raster layer to derive new output. So that's what we're, let me go back to the workflow. So here in our an analysis where we've just identified slope and aspect and reclassified those, we're next going to use the raster calculator, and we're going to take the reclassified slope and the reclassified aspect and add those together and divide by 2. And that's going to give us the mean slope and aspect on the same scale of 1 to 4. We're then going to bring in the reclassified land cover. And remember, that has 0s and 1s, 1 being suitable, 0 being non-suitable. So we'll multiply this raster by the reclassified land cover, and that will filter out the unsuitable areas based on land cover. And it basically gives us our first result, where we have now the areas that are most suitable based on slope and aspect, but only for suitable land cover types. So that we've incorporated 3 of the variables into our analysis. And then we'll use this Boolean operation in the raster calculator, greater than or equal to the threshold value of 3.5. And that will output our basic final result of areas that are meet our suitability criteria for slope, aspect, and land cover. We have two criteria left at that point. We have suitable soils being one. So we're going to do this operation to polygonize our final result to convert it from raster to polygon. And then we'll bring in soils. And soils is a polygon data set in our case. So we're going to select suitable soils using an expression. And then we're going to dissolve that polygon data set so that we get the suitable soils dissolved as one single polygon. And then we can use that suitable soils polygon to clip our polygonized vineyard locations. And now we have raw potential vineyards who are also now located just on suitable soils. So we have suitable soils, suitable land cover, and slope and aspect represented. And then the last thing is to bring in size. There was a criteria that it has to be greater than 1.7 hectares. So since this is polygon, it's easy to calculate the size of each polygon and filter out the ones that are less than 1.7 hectares. And we'll have our final solution at that point. So that's where we're heading here. So we'll next move into the raster calculator. So I can find that here in from the raster menu, raster calculator. And if we run it from here, let me mention this. If you go to the processing menu, we have the toolbox. So this toggles the toolbox off and on. We have this thing called the graphical modeler, which is something I'll briefly discuss. This is an environment that lets you drag and drop data sets and processing algorithms to create a workflow, make your own custom algorithm. So in fact, this whole workflow that we are going through could be set up as a graphical model that would just have an input of a DTM, land cover, and suitable soils. And you could then just have the whole process run as one operation. So that's a really nice environment. It's a different topic, but it's fairly intuitive to use. And it basically creates a processing tool from the model that you can use. Then there's history, and this is what I was thinking of here. So if I go to the history of processing, it opens up this processing history. So I can see that I ran slope and aspect, and then the 3 reclassified by table operations here. So if you select one of these, like the slope, it will show me the command line argument for running this, if you wanted to run it from the Python processing console. And if I double click on that, it'll open up the tool as I ran it. So that processing history is really important for remembering what it was you did on a project. And so if I run the raster calculator from here, it doesn't show up in processing history, but there's also the same raster calculator in the toolbox. There's this Google raster calculator that you can use. And so here it is. There's 2 tools. There's the Google raster calculator and the QGIS raster calculator. If you run it from the toolbox, it will show up in processing history. It's basically the same tool, but set up as a processing algorithm. And the reason that it's also in the toolbox is that if a tool is in toolbox, then it can be used in a graphical model. So that the modeler that I briefly described, you could bring in the raster calculator into a model because it's in the toolbox. So that's the only difference between the 2 tools, really, is that one will show up in processing history and the other will not. Otherwise, it's the identical tool. So I'm going to start by combining my reclassified aspect and reclassified slope. So I can, I'm going to enter some, let's see, I'll just start by slope reclassified plus aspect reclassified. And this notation here where it says @1, that is simply because these are single band images. And so they only have one band. If you had like Landsat imagery that has multiple bands, you could run, each one of those bands would be shown here as potential input to the raster calculator, and you could do different operations on different bands. You could in fact combine different bands in the raster calculator. So that's why we see that @1, that's what it means. So I'm going to wrap this addition operation in parentheses and then enter the division symbol and divide by 2. So I'm adding and dividing by 2. There is an option, this is actually a new feature, to create on-the-fly raster. So if you're doing a kind of a one-off operation or you want to just do a test, you can check that box to create a temporary raster of the result. But here I'll save my output. And I'll call this slope aspect mean. So that's essentially what I'm generating, is the mean, slope, and aspect. And again, you have controls for the extent, but we already have our data, which is we generated from aligned rasters, so we don't need to adjust any of that. And I can click OK. So here I have my slope aspect mean, and I can style this as a single band pseudo color from red to green, with green being the best and 1 being less ideal. So we can start to see the ideal locations for a vineyard popping out based on slope and aspect already. And now we'll bring up the raster calculator again. And I'm going to take this slope aspect mean and multiply that times the reclassified land cover, which again has values of 0 and 1. So I'll filter out the any pixel that has a 0 in land cover will result in a 0 in the output. So I'm basically going to be filtering out the unsuitable land cover types by doing this. So I will save this out as raw results. And click OK. And now if I style this as single band pseudo color, we can see that those unsuitable land cover types have been filtered out. So we're getting a clearer picture of where the potential vineyard sites will be at this point. And now we can do the final logical raster calculator expression. So here we have, again, results from 0 to 4. And we're going to say that if it has a pixel value of 3.5 or greater, then it will be suitable for a vineyard. So I can use the raster calculator to take this raw results and use this expression greater than or equal to 3.5. And this will produce a binary raster. If the value is greater than or equal to 3.5, it'll have a value of 1. If it doesn't meet that, it'll have a value of 0. So I'll essentially be pulling out the suitable vineyard areas of my from my raster this way. And I'll call this final result. And click OK. And now I can So let's style this as a paletted unique values renderer, just has zeros and ones. So I can make the ones have a green color and the zeros something different like red. So now I'm seeing the suitable areas in green and unsuitable in red. Okay, so I think the next step is to polygonize this. So we have essentially done what we need to do in the raster environment. And so we're going to convert this to a polygon because the next criteria that we're going to work with have to do with soils, which is a polygon data set. So I'm going to go to the raster menu to conversion, and I'm going to choose polygonize. You can see there's the opposite tool, rasterize, just below, but we'll choose raster to vector. And the input will be this final result. When you run this tool, it's going to produce just one attribute column. It's going to have the pixel value, and it by default gets called DN, which is short for digital number. You can name it anything you'd like. I usually just keep the default. And I will save this out to a shape file. I'll call it final result poly. And again, this is using this Google polygonize command line tool. And again, it's going to give you the corresponding command line expression if you ever wanted to run this from the command line. I'll click run. Always takes a little longer to convert to the vector data model. Okay, so that finished. And I have my final result here. And if I open up the attribute table, you can see it just has this one column, zeros and ones. So I'm really only interested in the ones. So I can select by expression and choose DN equals 0. And select those. And then I can just put this table into edit mode and delete those because I'm really only interested in the suitable areas. You can click save. And if I turn off some of these other layers, now I have a polygon of the suitable areas in terms of slope, aspect, and land cover. So are there any questions on what we've gone through so far? I think what we'll do, if there are no questions, is take a, let's take a 10-minute break, and we'll come back at the top of the hour, a 9-minute break. We'll come back at 11, and we'll finish up the analysis. I will show you some other related tools that we can use to do other tasks in the raster environment.
Sounds good.
Okay, welcome back, everyone. So it's hard for me to monitor the chat while I'm lecturing, so I missed Salek's question, and I will certainly cover this during the Q&A session next week too, but he had a good question. He asked if there's a library of color maps that are suitable for people with color deficiency. And there's a couple interesting features in QGIS for this. First off, if you go to the view menu and you go down to this section called preview mode, you can simulate several kinds of color blindness in QGIS. So I can simulate protanopia color blindness, no red. And this green to red color map is perfect for this, because this is a highly problematic color ramp if someone does have a color deficiency. No green. So we can see what this looks like, simulating different kinds of color blindness. So this is something that you can use if you know one of your customers or someone who's going to be reading your maps has a specific kind of color deficiency. You can use this preview mode to basically see what the map would look like for them and adjust the symbology accordingly so that there's enough contrast between different features that you want to highlight. There's also, if I, for example, go into slope aspect mean and I click the color ramp drop down and choose create new color ramp, I can choose this one color brewer. And I haven't looked at this in a while to see if this was in here. Maybe it's not, but there is a corresponding website that these color ramps can go with. It's called colorbrewer2.org. So here's the website. And this is a website that allows you to design color ramps. And one of the settings is colorblind safe. So you can use this to choose different kinds of color ramps: sequential, diverging, qualitative, the number of data classes, and it will output a color ramp that works for, in this case, colorblind or color deficient map readers. So this is another really good resource for that sort of thing. And let me undo to put this back. There's always this undo, redo buttons at the bottom of the layer styling panel so that you can undo something if you didn't mean to do it. So what I'm going to do now is add in the suitable soils polygon data set. So in the vector data geo package, there's this soils layer. This comes in pre-styled. One thing about a geo package is that you can store vector symbology in there too. So in this case, this comes in with the symbology and the legend already set up. And so we are interested in just certain soil types. And we can see this is using this attribute column tsim, which differentiates the different soil symbols. And we're interested in just 4 of these: the DL, the glacier meltwater clay, the DS, the glacier meltwater sand, and the ML, the clayey till. So we're just interested in those 3. Those are the 3 suitable soil types, and the other are unsuitable. So since we're dealing with a vector data model, what we can do is use the select features using an expression. And if we have soils highlighted. When we click this button, this select by expression window will open up, and this is just going to be for the, we can select by expression without having to open up the attribute table using this tool. You can also do it from the attribute table, of course. And I'm going to use, I'd already, let me copy and paste the expression. So we're going to be using the field tsim equals to DL, DS, or ML. So I'll select features and close. We can see the suitable soils highlighted. And then what I can do is go to the vector menu, to geoprocessing tools, and dissolve. So we can dissolve these selected polygons into suitable soils. So I'll just dissolve the selected features only. I won't choose any dissolve fields. So it'll just dissolve that selected set. And I'll save this out as suitable soils. And click run. So now I have a suitable soils polygon data set. I also have my final result poly. So what I can do now is use suitable soils to clip the final results so that I'll only have final results within suitable soils. Bring up the clip tool and clip the final result poly by suitable soils. And I'll save this. You could save this out to a geo package. I'm just choosing shape files. It's because it's easy while I'm demoing this. So I'll call this final vineyards, I think is what I was doing in the instructions, trying to match what I gave you. Yeah, final vineyards. Save and run. So here I have my final vineyards. Oops, got the wrong layer selected in the styling panel, so it didn't take. So there we have our final vineyard locations. And we have one more factor to consider, which is size. You know, so if we, since this is all resulting from raster data, when you zoom into these areas, some of them are just individual pixels. And we have a size criteria that has to be greater than or equal to 1.7 hectares. So we're going to use that to filter out the ones that are too small. So I'm going to right click on this and open up the attribute table for it. And I'll put it into edit mode and I'll add a hectares column. And for this, I'm going to make it a decimal number real. And I only need one decimal place of precision. I'm interested in greater than or equal to 1.7 hectares. So I'll just use a precision of 1, so it'll store 1 decimal place. I have my new column. And I can calculate this by using a geometric function in QGIS. So if I go to, yes, I have my, I want to set my target layer to hectares and then click this expression button. And I have my expression window. And if we go into the geometry section of QGIS, you can see there's this variable called $area. It returns the area of the current feature. So if I use dollar area, that would return the square meters of every polygon, but I'm interested in hectares. So I can just divide that by 10,000 to produce hectares. Go ahead and click OK. Dollar area divided by 10,000, and then I can choose update all. And we can see that we have 15 or 16 at least that will meet our size criteria. I can go ahead and save my edits. And I want to mention another useful plugin for doing this. I'm going to open up the plugin manager. There's a plugin called Calculate Geometry right here. And I already have it installed, but I'm just going to turn it on. So this is a handy plugin because it will allow you to calculate area or perimeter for polygons, length for lines, or X and Y coordinates for points quite easily. And all of this is possible just with the normal geometry functions in QGIS, but this just is easier because I can just right click on a layer and choose Calculate Geometry once that plugin is turned on. This is where it shows up. And then I don't need perimeter in this case, but I could choose my hectares column and choose hectares as the units. And you can see that all the common units are in here. So we can choose any unit that we need. We can even set the precision and click OK, and we get the same calculation. So it shouldn't have changed anything. It's working. Shouldn't take this long. Hopefully it's not causing a problem. Usually, you know, it's a fairly small data set. It shouldn't take any longer than the calculation from the attribute table. So I have a sinking feeling like it might be crashing QGIS for some reason, which I've never had a problem with this plugin, but I'm also, I just updated to the latest version of QGIS 3.24, so there might be encountering a bug with the latest version too. I think let me just open up a new version of QGIS and try to pick up where we left off here. Oh, good, it finished. I don't know why that took so long, but I should be able to open up my attribute table now and have the same results. So the final step in the analysis now is simply to filter this by the size criteria. So I can open up layer properties, go to the source tab, and this provider feature filter is where you can enter an expression to filter a layer. So I'll bring up the query builder and choose hectares greater than or equal to 1.7 and test it. So it returned 18 rows. And there we have our final selection of vineyard sites. So this is kind of, this is the answer you should get. And this is kind of what I would consider what they call a coarse filter analysis, where we've filtered the study area for suitable slope, aspect, land cover, and soils. and then meeting the size criteria. You would then have to look at parcel availability and there's probably some other, important criteria. But we know that all these areas would be suitable. And we can see that some of these, even though they meet the size criteria, are strange shapes. So they're probably not practical to have. Others are, much more regular polygons. So that may end up being a deciding factor in this too. Some other useful tools that could play into this analysis that I'm not actually gonna, it's not in your instructions or not gonna be in your assignment. Your assignment is simply to finish this analysis. But we also have this, basically our raw results here, which was incorporating slope aspect and land cover in this case. And so one thing we could do with this data set is bring in, I provided another geo package with your data called other data, and there's a parcel boundary layer in here. So I can add parcels for the study area to this. And it might be interesting to see the mean value of the raw results for every parcel. And so there's a tool called zonal statistics that we can use to get raster statistics by polygon. So if I go to the processing toolbox, I can search for zonal, and we see this zonal statistics tool. So this is going to take an input layer, and I can have my parcels clipped being the input layer, and the raster layer being this raw results raster. And then there are statistics that it will compute. So if I click this button, I can see that by default, it's going to choose count, sum, and mean, but there are others that you could choose. And I think mean would be the most interesting here to get the mean value in this raw results per parcel. So I'll just stick with these, and it'll by default include an underscore column prefix so that you can figure out which columns got added using this tool. I'll just save this out as parcels raw results. And click run. Drag this new parcels layer up to the top, and now we can symbolize it by that mean. So if I open up the attribute table for this, on the right, we'll see count, sum, and mean that were added to this table from that zonal statistics tool. So mean will be the mean raw result. So remember, this should range from 4 to 1. So I can style these using the graduated renderer based on that underscore mean column. And let's make these red, yellow, green, and click classify. So now we can see which parcels have the overall highest score. So this could be used in conjunction with the final vineyards to take a look at which parcels could be looked at as purchase to purchase the actual vineyard, and to see which which potential vineyard sites fall squarely within a parcel and which may involve purchasing multiple parcels to support the vineyard. So we can see some are better situated than others. So that zonal statistics tool is something that people often use in conjunction with a raster analysis to get results. We could do this for any of the raster data. We could compute the min and max elevation or the mean slope or any of those kind of figures for these parcels by running that against the parcels and the slope layer or the terrain layer. We could also use it to look at the land cover by parcel. So another thing that people often have to do in the raster environment is sampling raster values. And this is like for points, for example. So it's often the case where we just saw how to do that using zonal statistics against a polygon layer. But often people have points too, and they want to know what is the elevation of every point or something like that. So there's a number of ways we can achieve this in QGIS. There is a plugin called the point sampling tool that I'll show you. And this is really nice because we can use this with a point layer and get basically have the points intersect multiple rasters and populate the output with results from different rasters. So in this case, we have a layer of archaeological sites, and we may be interested in getting the mean elevation or the slope, elevation, and aspect for those archaeological sites. And so we can use this to intersect the archaeological sites with 3 different rasters in that example and output the result. There's also a sample raster values algorithm in the processing toolbox that we can use. This just works against one raster at a time. So the point sampling tool is a little more powerful than the processing tool from that regard. But if you only need one to intersect a layer against one data set, you can do that. This is, since it's a processing tool, it could also be incorporated into a model, which is another advantage of that. And then there's a function. So there's a raster value function in the QGIS toolbox that you could use in an expression to calculate the value for points from a raster. So let me show how these would work, and I'll add some data here. We also have, I have a couple point layers that you can experiment with. I have a buildings layer and archaeological sites for the study area. So let me install the point sampling plugin. Point sampling tool. So here we have this building points layer. I'll turn off archaeological sites. And we go to plugins, analyses, we see the point sampling tool, and it's also here as a button. So if I open this up, I can choose my point layer, like building points, and then I could choose different rasters to intersect that with. So I could choose, let's see. Why is it not showing me every single raster in here? It should be showing me the aspect and terrain rasters in here. I'm not sure why I'm not seeing those. So it shows you for the vector layers, all the different attribute fields that they have. Oh, here we go. Personal results raw. I'm not sure why it's not showing the, oh, it's because they're not turned on. That's right. So we have to actually have them enabled. So let me turn on slope and aspect and terrain aligned. That's the problem. Okay. User error. So building points is my layer, and if I scroll down, I can choose aspect, slope, and terrain aligned, and then I can put out a new buildings point layer. And I'll just output this as a geo package, buildings, and add it to the map. So click OK. So it'll run through. There's 3,500 building points here, and it finished. And if I open this attribute table up, it now has the aspect, slope, and terrain for each one of those, along with the feature ID. So if you want the other aspects of the attribute table, you have to select those from the menu too, but we can see that we were able to intersect this with all three of those, and it happened quite quickly. So that's what how that plugin works. I
have a comment. Could I have a comment there? There's a
course.
problem with that way it's working, because you don't get a unique value. You don't get what was in your original table.
Yeah,
so
I think what you have to
generate
do.
that. I couldn't find it. I actually used it yesterday.
Oh yeah, I think.
And it was very annoying, because then you have to connect it by like nearest neighbor or something. I wanted the data set from the original table put into the new one you generate.
Yeah, they've changed this plugin because it didn't used to operate that way. And
okay.
Let me see. I'm kind of stuck. I think you can choose the different building point attribute columns here to have them included.
Okay, I didn't find it yesterday, but maybe I should look more careful.
So you can see here, it lists all the different attributes for the building points.
Okay. Okay.
So I think you select those,
okay.
And then
it could be. I'll check out for the exercise. Yeah.
Yeah. I think that may be the way it works. But yeah, it's a very good point. If you can't just add those to the attributes of the layer, then it's not so great. We also have the other QGIS tool, sample raster values. So if we take that original building points layer here and we want to intersect that with terrain, we can save this out. So in this one, it should have all those columns. Yeah. So now it only lets you interact with one raster at a time, but it brings in everything and just adds the output. So here's the elevation added to that attribute table. So the sample raster values algorithm is, even though it only operates on one raster at a time, might be easier to use. And then, one of the real powers in QGIS in general, especially with vector data, is all the functions that are available. We already saw that you can have $area, for example. And if I added my archaeological points, so let me make these a little bigger so we can see them. There's not as many. Let's give them, no, that's not really. Make them yellow or something. So we have these turn some of this off. Okay, so here we have these archaeological point sites here. And if we wanted to know the elevation of those, for example. Another way we can do this is we open up the attribute table for these. We can create a new column. We can call it elevation. And now what we can do is set the source field to elevation and open up the expression window. And we can search for raster. And we see there's a raster value function. So we can use this to tell QGIS to calculate elevation to the raster value, and it requires the layer and the band. So I will go to my map layers and add terrain aligned as the raster layer. And it only has one band. And then we add the value dollar geometry. So if I'll show you where this is. Go into geometry. There's this dollar geometry, which is the geometry of every point, every feature. So that's what this raster value function takes: the layer, the band, and the point. So the layer we get by selecting the correct layer from our loaded layers, and it gives it this the name with this kind of long string that is QGIS's ID for this layer within the project. Then it has a one band, so this would be 1 by default, and then the geometry of the point. And we can see the output preview down here is a sample elevation value. So I can click OK and update all, and it calculates the elevation for our data set. Extracts the value from the terrain for every point into that column. So that's another nice feature, is the raster value. And I think there's also actually that raster statistic, which is a related one. So if I open this back up and again search for raster, there's raster statistic, which would allow you to extract the min, max, average range for values out of the raster. And in case you haven't used this expression dialog much, there's also a recent section down here. So we can see recent expressions that we've just used this morning. So you can always easily recall those. And if you ever develop an expression that is particularly complicated and that you'd like to reuse, you can, from these buttons up here, import expressions or export an expression. So you could export this expression out as a .json file and save it and be able to reuse it or pass it on to a colleague or something like that. So that's just a general QGIS feature that allows you to save expressions that you've used. Okay, so another thing I wanted to cover is interpolation. So let me open up another project. So interpolation is where commonly you have a set of points and you want to generate a raster surface from the values in those. And this is how digital terrain models are generally produced as well. So I'm going to go, I have an interpolation project that I want to open. So this is kind of a short exercise that actually comes out of my QGIS for hydrological functions textbook. And this is a series of weather stations in the Netherlands. So we're in the Netherlands now. We've moved from Denmark down to the Netherlands. So if I zoom out a little bit, we can see where these points lie. So here is Denmark and the United Kingdom, and our points cover all of the Netherlands. And I have them symbolized based on this Celsius field. So it's the temperature in Celsius. And we have the symbols broken out to a red to blue color ramp, blue for the cooler colors, red for the warmer colors. So if we want to generate a temperature surface from these points, we would be using one of the interpolation tools. So we can use a couple different tools from the raster menu. These are going to be in the miscellaneous. No, they're not miscellaneous. Where are they? Analysis section. So raster analysis. And we can see these grid tools. So there's one called grid nearest neighbor and one IDW. So if we run the nearest neighbor against this station layer, we can set this up as, let's see, I remember how to do this. I think we can use the defaults for these. You can always tweak these, but I think for just getting a basic result out of this, we just need to save it out to a file. I'll just call this nearest neighbor. And the Z values are going to be from the Celsius column. That is the one important parameter there. We can enter node data values. So we could put in a -999 in here for node data. Let me just see if I go ahead and click run. Yeah, it creates this nearest neighbor interpolation. So, you know, nearest neighbor is going to produce something that looks more like polygons, but in some cases can be considered more correct. We can see if we use a green to blue color ramp, or red to blue rather, that we get these, we have to invert it. Yes. So we get the warmer colors for the warmer areas. So this is basically assuming that what is close to the station closest to the pixel has the most bearing on the temperature of that surrounding pixel. So it generates a surface that looks like this. And there is also a related function called inverse distance weighting. If I go to analysis and choose, it's this one, I think they renamed it. The point layer is going to be the stations. And the Z value is Celsius. And I'll save out the result as IDW. And the inverse distance weighting produces a smoother looking raster. And so there's multiple ways to do this. There's also something called kriging, which is more involved, but allows you to generate a surface from points. So with these, you know, this is kind of just a quick introduction to the tools. You have to do some careful thought and experimentation when using these and come up with the technique that you think is giving you the best results for your particular use case. But the tools themselves are fairly easy to use. I need to invert this color ramp. There we go. The warmer colors being off the coast. So that is another thing I just want to show you is how to find and run the interpolation tools. These are also in the processing toolbox. So if you search here for interpolation, you'll find an interpolation tool set here with several tools. Some of these are very new and I haven't used them yet. So these are, for example, line density is a brand new processing algorithm. But you can see there's quite a few in there to experiment with. And another thing I can show you is that there's just a renderer for this in QGIS. So if I turn off all my raster layers and just have the points, I can render these as a heat map. So I can choose the heat map renderer for these points and choose the same red to blue color ramp. And I can choose to weight the points by the Celsius field. And I have to increase I think I have to increase the distance here quite a bit because I don't have a very dense array of points. And I must admit, I've never tried this renderer on this data set. It just occurred to me to try it. So I might. Not sure why it's not giving me a result. I actually use this in my data visualization class against some more dense point data, and it works quite well. Let me go back here and show you what it looks like with the building points. I think I've got a more interesting result. So if I use heat map here, oh, I meant to run it against the buildings, not the archaeological sites. There we go. So now we're getting a heat map for these. And you can choose if we had, a number that we wanted to use to weight these by, we could. If we had, if you have towns and you have population, you can weight the heat map by population. So this is another just renderer that can allow you to quickly generate a heat map based on data, just in the way the data are rendered. And sometimes this can be a useful way to just explore your data because it's very quick to use and can give you, pretty much immediate results. And then you could also just, from there go and generate a interpolated surface using the tools I provided. But this is kind of an interpolation just in the way the data are being rendered in this case. Let's see the. So are there any questions on any of these other tools that I discussed or the analysis itself that have come up?
Yes and no. I think you should look into the calculation of your hectare. You used dollar geometry. No, you used dollar area. But there's another function using area dollar geometry. And I think, well, it's hard to explain. I think it's about if you're calculating it spherical or cartographical. So
Right.
you get two different values. You should be very aware of which one you're using. It's not, the differences is not very high, but in our company, we had decided to use area dollar geometry to calculate the areas. Because when you use UTM here in Denmark, it is on a flat card you actually calculated. So there's
Right.
2 different ways of doing the calculations. You might not see it with only 1 decimal. You might have to add a little bit extra.
So you're
But
using,
there's one called area, yes, and then dollar geometry.
yeah.
Mm.
Yeah, so area. The area calculated by this function respects both the current project's ellipsoid setting and the area unit setting. And then there's, like you said, dollar geometry. But yeah, that's a very good point. You certainly will get different results depending on which ellipsoid you are computing area against. And
Yes.
if you are, depending on the kind of precision that you require, it's important.
Mm.
So yeah, thanks for that. That's a good point. Okay, so that's all the material that I wanted to cover today. We're about 10 minutes short. So if you have any other questions, I'm happy to take those. But I will be sending you the recording and the assignment, and we will have our second question and answer period on next Thursday at the same time. So you can check in then if you encounter any issues or have other questions come up over the next week.
Hi. I have a quick question. So I don't know if you can hear me.
Yes.
Yeah. I had to run out on a errand. But I had a question earlier in the chat about whether there is a library of color maps that are good for people with color vision deficiency or colorblind people. Because if you use, like a red to green map, then that's a significant part of the population that can't actually read it.
Yeah, and yeah, thanks. I did cover that, but let me show you that because it's fairly quick to do. So one set of tools that you can use for that is from the view menu. There are different preview modes. So there are different preview modes for different types of color blindness. Protanopia, deuteranopia, and tritanopia. And so you can use these to put your map into that context so that you can see what a colorblind person with that condition how they would see the map. And then you can adjust your symbology accordingly so that features have enough contrast and the right features are being highlighted.
Right, that's extremely helpful, actually. Thank you.
And I
that's
also
a really good feature.
Yeah, it is. It's fantastic. And there is also a website that I showed called Color Brewer, and I put the URL in the chat, colorbrewer2.org. And this is a nice site that allows you to develop color ramps. And one of the checkboxes you can enable is colorblind safe. And from there, you can choose different types of color ramps, whether they be diverging, qualitative, sequential. You can choose different hues for these. And it will generate a color ramp based on your selections and give you the hex values or the RGB values or the CMYK values for those so that you can use those. And you can also export these out as I think JSON files or something like that, or CSS. So this is a great site, a really nice resource when you have kind of some challenging cartography and need to develop a special color ramp for a specific purpose. This can be very helpful.
Right, that looks really good. Yeah. Okay, thank you.
Mhm. Okay, well, thank you, everyone. If you have any other questions, feel free to email me, or we can meet a week from now to discuss those as well. And I'll be sending out the assignment and the recording. And with the assignment, I'm going to ask that you finish this. Let's see, by the 28th. No, that's not right. Oh, by the 7th of March, Monday, the 7th of March. And you will also be receiving a certificate for the course when you turn in that assignment. So if you haven't turned in the first assignment, please do so as soon as you can, and get the second one to me by the 7th of March so that you can get your certificate. And yeah, thanks. It's been a great class. This is actually the first time it's been taught. So if you have any other feedback or other things you'd like to see covered, please let me know.
Okay, thank you.
Yeah, thank you very much.
Hey,
Thank you.
Bye.
have a good weekend.
You too.